Hi everyone, welcome to this video. This is part of the Maxx-Solar Solar Power Designer Backup course. This is an ideal course if you want to learn more about solar either for your own home or business, or if you want to be part of the solar industry and design and install solar power systems. In this module we will talk about different system configurations, so on-grid, off-grid, AC coupled, DC coupled, and all the different combinations of systems that's possible and how it interacts and connects with the grid and energy storage systems. Great, so let's dive right in. Great, so let's get into different system configurations of solar and backup power systems, or in other words, different types of solar systems, solar PV systems. But before we do that, let's have a look at a few symbols that will be used so that we're all on the same page and we know what symbol stands for what. For example, PV modules will use this symbol or this drawing. Inverter will be represented with this symbol. For example, with direct current on this one side represented by that and that symbol, and alternating current by this symbol, and it converts between direct current and alternating current and vice versa. BESS stands for Battery Energy Storage System. And that's basically a battery combined with an inverter, and your loads will be on this side, and with bidirectional flow of energy between your loads, inverter and battery, inverter and loads. Wind power with this symbol, generator like this, energy meter with this symbol, consumer loads by this picture of a house, and large consumer loads by this picture of industrial buildings, a factory or office building, and the grid with this symbol. Great, so that's just some of the symbol that we'll use in different configurations to represent the different system configurations of PV systems. When we talk about solar and backup power system configurations, we must talk about how it is related to the electricity grid. We talk about the term grid quite often, but what do we actually mean with this term? The grid is a network of interconnected power generation, transmission and distribution systems that enables the transfer of electricity from power plants to consumers. The grid encompasses various components, including power generation sources such as thermal power plants, hydroelectrical plants, wind farms and solar power plants, high voltage transmission lines, substations, transformers and distribution lines. Basically, all the infrastructure that facilitates the delivery of electricity from generating plants to homes, businesses and industries. Okay, so solar systems can be configured in several ways to fit into the existing electrical infrastructure, and it can be basically divided into two main categories: on-grid or off-grid. On-grid just means it connects to a grid where it can either charge batteries from the grid or supplements the load from the grid, or export energy to the grid, where off-grid is just there's no grid available to connect to and it can't interact with the grid. Great, so this diagram gives a nice overview of the different system configurations that's possible of PV systems. So two main categories, either on-grid or off-grid systems. Under on-grid we've got four different types. Systems designed to just export energy, systems designed to cover your base load with solar power, PV farms, large solar power systems, on-grid systems with backup power, and then on the off-grid side we've got either AC or DC coupled systems, and then water pumping systems. So this course is mainly about on-grid systems with backup power. And the main components of that system is your solar modules, then either a string inverter or charge controller. String inverter if it's AC coupled, a charge controller if it's DC coupled, your inverter charger, and the battery and the grid connection. Great, so let's get into more details of the different configurations of solar systems, of on-grid and off-grid systems. So on the grid we've got just normal grid-tied on-grid systems, or on-grid with storage and backup power, And then off-grid, we've got DC coupled and AC coupled that we'll go into more detail with. So firstly, PV on-grid configuration. Basically, you've got your grid, then you've got your utility meter, and then you've got your house loads, and then a grid-tied inverter is installed in the house, and solar panels is connected to the grid-tied inverter. The most simple type of setup, very few components, just a solar panels and inverter connected to the loads. So if the solar panel generates more energy than what the house is using, the extra energy will just go back to the grid. And if the house is using more energy than the solar system is generating, then it will just pull that energy from the grid again. Okay, so this is what a visual representation would look like of a grid-tied solar system. Your grid PV array on the roof, connected with DC wires to your inverter, connected to the house and to the grid through electricity meter. To summarize, the solar PV is converted to AC power and coupled to the grid or synchronized to the grid. The solar system complements grid electricity, so the house uses electricity from the grid and from the solar system. And the solar system supplies part of the load. The rest of the load is supplied by the grid, or it can even also export if it generates more than what the house is using. And also when the house is using more than what the system can supply, the rest is just supplied with the grid. The system can be either single phase or three phase, and systems bigger than 5 kilowatt would typically be three phase, whereas systems smaller than that is normally one phase. Okay, the second type of system that we'll have a look at in more detail is on-grid with storage and backup power. So it's the same as a normal grid-tied system with your solar array, your inverter connected to the house, but there's also a battery system that comes connected to the system. And energy flows to the battery and from the battery depending on the loads and the amount of energy generated by the solar system. And this is a AC coupled system, so the solar energy is coupled on the AC side. So instead of the DC side, that's what is also option. So your solar array DC is converted to AC, and on the AC output, the energy can flow bidirectionally to the batteries and out from the batteries to the AC loads. Great, so let's have a look at off-grid systems. Off-grid systems basically divided into two types, either DC coupled or AC coupled. So off-grid systems have been implemented since the early 80s and has played an important role in countries where the grid does not reach every household and business. They would be cheaper to install a solar system than to extend the grid to remote places. Okay, so the first type, DC coupled, basically the PV is DC coupled. So on the DC bus or the DC side of the system, the solar is connected there through a charge controller and charges the battery, and energy flows directly from the panels into the battery or from the panels through the inverter to the loads if the battery is full. Typically the solar panels are up to 250 volts all connected in series, and the work of the charge controller is to bring that down typically to 12, 24 or 48 volts, and where the inverter then makes it to 20 volt AC. And if you look at that in pictures, this would be your solar array connected in series with each other, the panels connected to your MPPT or your charge controller, and then the higher voltage of this panels in series is converted down, in this case, to 12 volts, and then the power flows either directly through the inverter to the loads or to the batteries. Great, so let's have a look at the second type of off-grid system that's called AC coupled. So again, as it's off-grid, there's no grid. the PV energy source is not connected directly to the DC bus through a charge controller, but it's connected to the AC bus through a grid-tied inverter. And you also got a battery inverter here. So you've got two different types of inverter. Your grid-tied inverter, which converts the power from the PV into AC, and your battery inverter, which converts the DC power from the battery into AC. Basically, this battery inverter generates a frequency, a fake grid or temporary grid, that this grid-tied inverter synchronizes to. And then power flows from the PV panels or PV array through the grid-tied inverter, gets converted to AC, and then flows directly to the loads, and or through the battery inverter into the batteries. Optionally, one can also have a generator, where the generator AC power created by the generator will be converted into DC and stored into the battery. So if we visualize that in pictures, this would be your solar array, several panels connected into series that can create up to 800 volts for grid-tied inverter. And the grid-tied inverter will then convert that high voltage DC into AC power, 220 volt AC. And that is connected to this output frequency of the inverter. And the power will flow through the battery inverter into the batteries, or will flow on the AC side directly to the loads that's here. And optionally a generator, which can be started to charge up the batteries as well. One disadvantage of the system is that if the battery goes flat for any reason, then your battery inverter can't start up, and it can't generate a grid for the PV grid-tied inverter to start up as well, and then the system will be dead and it can't start up even though there's sun, just because the battery is dead. In that case, the generator will need to be started and the batteries will be loaded, charged up, and only then can the battery inverter start up and the system be started again. So not ideal configuration in very remote locations. One would preferably add a DC coupled solar as well to charge the battery in case of the battery going too low ever. Great, and this is what a picture of a system like that would look like, where you've got your grid-tied inverters, your battery inverter, your battery bank, and your generator. Obviously, the generator will not be started there, it's just a storage space for the inverter, for the generator. It will generate a lot of heat if it's ever run there, and heat is obviously not good for lead acid batteries, so it will be put outside and then started up and then charge up batteries in case the batteries ever goes flat. Let's differentiate between on-grid and off-grid systems. Firstly, on-grid. If electricity is supplied and bought from an electricity supplier, then the PV system is considered on-grid. If another party other than a consumer is involved in providing power, then the consumer is considered on-grid. So unless the electricity is completely isolated from the electricity supplier's grid, the system is considered on-grid. So if it connects to a supplier's grid, then it's on-grid. Off-grid, in the absence of electricity supplier, all power generation is considered off-grid. If all power generation belongs to the consumer, then it's considered off-grid. This is also an interesting example where you've got off-grid and on-grid on the same site. For example, all your heavy loads like the stove and oven is connected to the grid, national grid, electricity grid. But you've also got a off-grid system here where you've got solar panels, a charge controller, battery, inverter, and your distribution board, and it supplies all the lights and plugs of the house with off-grid electricity. So this part of the electricity supply is off-grid, and the heavy consumers like the stove, oven, and even geyser is on-grid. Good, so let's have a look at PV on-grid systems and how the energy flows in a system like that. So as we've seen previously, this is your PV array connected to your inverter, connected to your loads, connected through the energy meter to the national grid. And as we know, if the PV generates more energy than what the load is using, it's just exporting the inner energy. So let's have a look at what that will actually look like. So say this is the load profile of that building or factory. At night time it's about 20 kilowatt, and then as they come in for work, switch everything on, it goes up to about 50. Maybe that's tea break, and then lunchtime also the power consumption goes down, and then up again for the afternoon shift. Great, and this is typically what your solar generation profile would look like. So it's about around 7 o'clock, the sun will start coming up, going higher in the sky up until 12 o'clock noon, where you've got your highest generation, and these gaps would typically be cloud cover that goes over the solar system, and the sun going down again here around 7. And if we overlay your consumption profile and the solar generation profile on each other, it would look like this. So if we deduct all the solar power generated and just have a look at what power the grid need to supply, it will look like this. And all this areas in the light red area would have been covered with solar. And you can see here 12, the solar system generated more than what the consumption was like, and then it exported that extra energy to the grid. Good, so let's just summarize the different system configurations. Firstly, PV on-grid. That's the most common configuration, the most simple system. We've just got your PV array connected with your grid inverter, connected to the loads, and connected through the grid with an energy meter. This is the most common configuration, but if the grid fails, then the system also fails. It can't work without a grid, as it needs a grid to synchronize to. So what you can get then is PV on-grid with storage and backup, so that if the grid fails, then it's got the energy storage and the PV system can basically operate independently of the grid. So that's also got the advantage that it increases your self-consumption of solar energy. So instead of having to export the energy when there's more than what you're using, it gets stored in the battery for later use. Okay, and then finally PV off-grid configurations. So there's no grid, and in the case where there's not enough solar power, then energy can be supplemented with a diesel generator. And yeah, so also using solar power rather than diesel in off-grid situations, there's a lot of cost savings, especially with the way that diesel prices are increasing. Okay, so that's the end of this video. Hope you found the information interesting, helpful, or useful. If you did, please click the like button and please subscribe to keep on getting more content like this. Hope to see you in the next video.